Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to introduce Matthias SCHÖTZ, who is my postdoctoral fellow here at IMPAN, and he will tell us about his new achievements, that is associativity and commutativity of partially ordered rings. So let us hear the whole story about this partial order. The floor is yours, the Zoom is yours, take it away.
Thank you. Thank you very much for the nice introduction, and thanks for giving me the opportunity to speak here. Yes, the end of the talk you see here, the idea is that there are some quite old theorems, actually, or results that that tell us that certain partially ordered rings are automatically associative and commutative. So one does not have to, one does not need the assumption of associativity and commutativity in the axioms, because of course, in the end, one wants them to be at least associative. And it turns out that these different theorems, they just, in many cases, admit a common generalization. That's what I'm interested in. So
You're now muted. Hey, you muted yourself.
No.
Well, you were muted. Now you unmuted yourself.
So now we unmuted?
Yeah, it's unmuted.
Yes, now
Okay.
you're unmuted.
Okay, thanks. So after a small history lesson, I will present the general theorem. And then we go back to some applications, basically reproving all these old results with the new theorem. And then if there's some time left, I will also try to explain the proof to you. So, before we start, we of course need some basic definitions. So most of the time, we will be considering partially ordered rings or partially ordered real algebras. That doesn't really make a big difference. So the basic ingredient we need is partially ordered abelian group, which means, well, an abelian group with an order relation, a partial order, which is translation invariant. And in that case, we write G plus for the submonoid of positive elements. And then one basically knows that this submonoid that carries the same information as the order relation. And analogously, we can define partially ordered real vector spaces. Well, it's basically a partially ordered abelian group, but with the additional axiom that the multiplication with positive scalars preserves the order. And one additional ingredient that will be very important is the notion of an Archimedean order. And in this case here, a weakly Archimedean order. So we say a partially ordered abelian group is weakly Archimedean if the following holds. So if we have some positive element, so if for any element G of the group, there exists a positive element H such that minus H is less equal than n times G, and this is less equal than n. And this, if this holds for all natural numbers, then we expect the G to be 0. Well, how can we think about this? What is the heuristic behind it? Basically means there are no non-zero infinitesimally small elements.
So this H should be universal, yes? Or is it somehow dependent from G?
It may be a different H for any G. So if for a fixed, so we say that the order is weakly Archimedean if the following is true for every G. If there exists an H that might depend on G that fulfills this relation for all natural numbers, then G is 0.
Mm-hmm.
So H may depend on G.
Okay.
And
So may I comment?
Yes.
So since this is only a partial order, it must be so that H bounds something from two sides. In the linear order, it would be maybe enough to take one H, but
Yeah.
not for arbitrary.
Yes, and well, this heuristic that this means that there are no infinitesimally small elements. Well, in the abelian group case, this is not so obvious, but if we say we have a partially ordered real vector space, then of course we can make some changes. We can just multiply the whole inequality with 1 over n, and then this basically means, well, this is crossed out, and here we have a minus 1 over n, and here we have a 1 over n. And this way it's clear, basically.
Do you have a division in this group?
If we assume we have a real vector.
Okay.
In this special case, we can make this change, and then it's clear, well, if G is between something that can become smaller and smaller, then the G should be 0. That's a very natural assumption, I would say. It's just a little bit, well, not unintuitive to formulate it in the abelian group case. Okay, and I should warn you, there exist also similar notions. Okay, this is clear because this is called weakly Archimedean, and maybe there's also a strongly Archimedean. But unfortunately, different authors use different names, and it's a whole mess. We will need only this one version throughout the whole talk. So I hope we can avoid all the confusion that exists in literature. And I recently learned that very similar notions also exist, well, obviously, if you write your abelian group not in an additive way, but in a multiplicative way, well, you can just reuse this statement, but then people call it completely different. And the conclusion is even bigger. But let's keep it simple, let's keep it like this. So the first of these old theorems is due to Wernicke, Klein, and Tofpin. So 1941, it's well, approaches its 100th year anniversary. And the theorem goes as follows. If we have a weakly Archimedean partially ordered real vector space, and just a bilinear multiplication, so no assumption of associativity or commutativity, and we make some easy additional assumptions. The product of two positive elements should be positive. Makes sense, I would say. We also assume there's a multiplicative unit. So even without associativity, this unit is unique. And we also assume that this multiplicative unit is an order unit. And this means basically some multiple of it dominates every fixed element. So for every element A from the algebra, there exists a natural number such that A is less equal than N. And if these three assumptions are true, then they showed this product is automatically associative and commutative. And well, basically for them, this is not their theorem, this is more an observation. So what they did is they proved a representation theorem. So they proved that such algebras can be represented by continuous functions on a compact Hausdorff space. And they just noticed that their proof just does not need the assumption of associativity and commutativity. And then by the representation in the end, because after the representation, after this faithful representation, they get an associative and commutative algebra. Well, the original algebra had to be associative and commutative too.
But sorry, this is still purely algebraic. So no topology, no.
You don't need any additional assumptions. So
the concept of observation was in topological algebras, but the result is completely algebraic.
Yes, but you could say that somehow this multiplicative unit, this is an order unit, that kind of gives you a norm on the algebra.
The norm?
Well, you can use this ordering to define a norm. So you could say the norm of A is, well, the infimum of lambda such that A lies in between minus lambda times unit and plus lambda times unit. This you can show gives you a norm and very well-behaved one. So the statement is completely algebraic, but the proof is not. Let's put it like this. Well, actually, there exist, I think, multiple proofs. Some would be called algebraic, and I think theirs is actually algebraic, but you could find analytical proofs too. And now this, I think that's surprising. I mean, the assumptions are very weak. And of course, we know there exist non-commutative, non-associative algebras. So just let's think of one counterexample that shows that this order unit assumption, that this cannot be dropped. Think about it for a second. Everyone knows an example, well, the matrices, of course. So if we take the 2 by 2 real matrices and we use the entry-wise order, so maybe not the more natural one, where positive semi-definite matrices are positive, we use the entry-wise ordering where only the entry-wise positive elements are positive. And we consider matrix multiplication on it. Well, it's associative but non-commutative. This is a real algebra. It's weakly Archimedean because this entry-wise ordering is weakly Archimedean. Of course, the positive elements are close in the multiplication. We have a unit, but this order unit assumption is not true because the unit, well, it has some zeros in the off diagonal. And if you want, this is the most complicated reasoning for why the identity matrix in general cannot be the matrix with every elements 1 that maybe the first semester student might expect. Okay, so that was the first of these old theorems. Now we go to the second one. The second one is, is about the lattice ordered case. So we have to talk a little bit about these spaces. So Lie space is a partially ordered real vector space in which the supremum and the infimum of any 2 elements exists. And then the typical notion, the typical way to write this is this, V sign for the supremum and the wedge for the infimum. And in Lie spaces, we can construct for every element a positive and a negative part. Positive part is just the supremum of R with 0, and the negative part is the supremum of minus R with 0. And now maybe if you don't have a good intuition for Lie spaces, there's a very easy example, and this will be completely enough to remember this example to go through the whole talk. Namely, the standard example for Lie spaces is continuous functions on a compact space with the pointwise ordering. Maybe let's make just a short drawing here. If we take just the continuous functions, maybe on a real line, we have some continuous function R here. Then, well, if you go through the details, one finds the supremum of 2 elements is the pointwise maximum, the infimum is the pointwise minimum. This means this positive part, well, it's the pointwise maximum with the 0, so the positive part of R would just be this. Something like this. And the negative part of R would be, well, minus R, and then just the same procedure, so something like this. Okay, and there exist some representation theorems for Lie spaces that basically say that all the intuition for Lie spaces that you get from this example, they are typically true. So don't have to worry too much.
So in your example, this order comes from the order of values.
Yes.
Values are real numbers and it's a pointwise comparison function. Are there some other examples of these spaces not coming from this example?
Well, basically, I think this theory of free spaces was developed to get an abstract approach to measure theory and integration theory. So the next important example would be measurable functions or integrable functions. It's still the same thing. Okay, and then if you really want something that's not real valued functions, you can take can take R2 or any Rn with the lexicographical order. Okay. So then you have a total order. This you have supremum and infimum, it's just maximum and minimum. And well, these are non-Archimedean. So basically, in the non-Archimedean case, one really has some counterexamples. But in the Archimedean case, there really exists strong representation theorems. And I think basically the Archimedean case, what you can have is functions, well, not real valued functions, but extended real valued functions. But really, then that's it.
And that's it.
Yeah.
Okay.
So these representation theorems are really strong. Okay, the example we just discussed. Supremum, infimum are point plus maximum, point plus minimum. Okay, then the small, maybe obvious exercise in relation with this definitions here. These are called positive and negative part. Well, they are by definition, they are both positive elements because they are both the supremum of something with the zero, so that will be greater than zero. But why is the difference of the positive and negative part, well, the original element R? And the infimum of R plus and R minus, this is zero. I think that is very clear from the picture I just gave you, but well, from the axioms, it's easy, but it's maybe not so obvious. And let's just as a small exercise, let's go through this. So the first thing we have to remember is the ordering is translation invariant. Okay, it's a little bit more difficult to write here than on a blackboard. What does this mean? Well, for our supremum and infimum constructions, it means the supremum of A and B plus some C equals supremum of A plus C B plus C. And of course, we have basically the same statement for the infimum for the wedge too. The second thing is basically, well, multiplication with the -1 that reverses the ordering, and this basically means it turns the supremum into an infimum. So we have R wedge S. Oh, I'm switching from ABC to RS is minus R V minus S and a minus in front. So these statements, they follow immediately from the exits. So, and what do we do then? So what is this? R minus plus R? Well, by definition, R minus is the supremum of minus R and 0. And we add R to it. And so you could already see what we get. Minus R plus R is to 0. So we use this first property, which 0 plus R is R. It's R plus. So this gives us the statement R equals R plus minus R minus. And the last thing we need, the infimum of R plus and R minus. What is this? It's R plus was the infimum of R plus is the infimum of, no, it is the supremum of R and 0. I'm really confusing myself. I find these first steps in respaces really funny because the proofs are one-liners, but they are never obvious. I'm not sure whether I'm boring you and you already know the answer now. No. So what did we show? R plus is R plus R minus. Take the infimum with R minus. Now we can move out to R minus. So we get R wedge 0 plus R minus. And the R wedge 0, now we can use the -1 trick. It's the minus. Is there a question, something like this? R wedge 0 is minus R V0. And now, by definition, this first part here was our negative part. So this was the negative part, R minus. So what we get is 0. Okay. And there are dozens of these seemingly easy relations that you have in these spaces. I'll make it bigger. Oh. Well,
There's funny property of this line number 2. And so this action of the minus, this reflection, with respect to the lattice structure, acts like a negation, like a complementation.
yes.
So I wonder which part of this is of these results rely on the Boolean structure, and which part is real vector space part, because it's an interaction of these two structures.
I think there I cannot give a good answer. So what I've shown you that would also work for lattice ordered in groups. Yeah, we never used the multiplication of real numbers, but okay. Well.
So probably this positive cone is interpreted in a Boolean terms, because for instance for these 0, if you take the supremum of 0 and R, you obtain R plus. If this 0 is this minimum, okay, then it's simply R, which means that R is positive. Okay. So probably you could interpret in Boolean terms only this positive part somehow. But okay. Sorry for it.
Maybe if you restrict to, if you have this intuition of now measuring functions, if you restrict then to the not to all the measurable functions, but only to those that have values 0 or 1, then basically, well, the restriction of the space structure would give you the standard Boolean algebra structure, right? So yeah, they are clearly. That's better.
In general, you could take
Related
functions taking values in some algebra generated by idempotents, commutative idempotents.
Yes.
So could be reals, could be something else.
Okay. Okay. Now the second of the old theorems. We need a definition of an F algebra. So an F algebra is a Lie space with again bilinear multiplication, and well, again we need some additional assumptions. Product of positive elements is positive. That seems to be something that unites all these theorems. And something else. So whenever we have two positive elements, so that their infimum is 0, then we want, well, that the product with, well, C of A and then the infimum with B, which should be the same thing as the product with of A and C and infimum with B, then this is 0. And we want this to hold for the positive element C. Okay, I mean, this is, I think, an assumption that is at first sight strange, hard to interpret. But I think there is a good interpretation. So basically, why are they called F algebras? The idea was to find an abstraction of algebras of functions in the lattice ordered sense. And now what this means is basically, well, if these are Lie spaces of functions, then A wedge B equals 0 means you have two continuous functions which have, well, disjoint support, or maybe rather the interior of their supports is disjoint, to be precise. And then this means something like, well, so if the interior of the support of B does not intersect the support of A, then we want the same holds also for the support of the product of C and A and for the support of the product of A and C. So somehow this, I would interpret this condition as saying, well, the product may not move the support, right? But, well, as it is, it's basically just one abstract axiom for what people call F algebras. And now what the proof is, well, every weakly Archimedean F algebra is automatically associative and commutative. And that was the first result of this type that I learned. I found that also quite surprising. And okay, now the history is, I think, not so clear. I think the oldest reference for this result is a PhD thesis of a, well, apparently Japanese PhD student, Amemiya, 1953, but I cannot read his PhD, so I cannot check this. And, well, I think these here, Bernal, Bilkov-Pierce, these are the later proofs that you can find, and they are in English, you can read these papers. And what people also did, well, they then generalized this result from the lattice ordered vector spaces to the lattice ordered groups, and maybe also to other different settings. And the original proof is probably representation theoretic, and then people asked, well, are there more explicit proofs just using the population rules in Lie spaces just obtain this result, and they exist. So that's why there are a lot of references for this result.
Sorry, Thomas, may I ask you a trivial question? What this F stands for? F algebra, F is for what?
F is, I think it's just for functions. So the idea is that this is an abstraction of an algebra of functions.
Okay, so F like function algebra.
Yeah.
But
And again,
okay.
basically like before, this result that basically came up because people were able to prove representation theorems for these F algebras. And it turned out that these representation theorems never need this assumption of associativity and commutativity in first place. Get it basically through the representation.
I have a question. In this definition of an F algebra, everything depends only on this positive part, A plus, which is closed with respect to this multiplication. All these conditions depends only on these positive elements. Yeah. So you could speak not about R vector spaces, you could speak about some cones instead.
True. We will come back.
Multiplicatively closed cones.
You could basically say, that was also true for the first result, you could basically say they are not, maybe not results for ordered rings, they are more results for, well, semi-rings. Basically, well, additive monoid and a multiplication on top. Okay, and there's also a similar notion, almost F algebras. Let's go through this very quickly. Almost F algebra is again a respace with bilinear multiplication. Again, the assumption order of positive elements is positive. It's really something important. And now the simplified assumption, well, if we have two positive elements and their infimum is zero, then their product should be zero. I think thinking of functions is again very natural and a very, well, much easier or easier to visualize axiom than for the F algebras. And it turns out, of course, the name suggests that every F algebra is an almost F algebra, but the converse is not true. And what people were able to prove is every Archimedean F algebra is commutative. That doesn't make any sense.
Commutative means commutative or associative commutative?
Means commutative.
Not necessarily associative.
Not necessarily associative.
Okay.
So, of course, I wanted to write every Archimedean almost F algebra is commutative. Now, to your point, this is very important. One cannot prove that the Archimedean almost F algebras are always associative. This is exactly... Oh, my scribbling goes away with the next slide. I didn't know that. This is exactly this next counterexample. If you take, well, continuous functions on the interval and define the multiplication in this strange manner, so somehow it only depends on the first and on the last value. Product of A and B is, well, the sum of A0 times B0 plus A1 times B1. Okay. Well, it's clear. Product of positive elements will remain positive. That's true. And well, if the two functions have, well, disjoint supports, then of course, well, either A1 or B1 or A1 and B1, there will also always be one that is zero. So the second axiom is also fulfilled. So this is an Archimedean almost F algebra, but it is quite clearly not associative. It is commutative, you see this.
But why is it essential that the functions are continuous?
It's not. It's just the typical easy class of examples that I think people like to think about.
Okay.
Okay, here you see I think the history is again even trickier, vastly tricky. This is some preprint at the University of Tunis that I never could find, but this seems to be the oldest reference, and there are others that you can find and read. And here the paper by Sheffield, this is older, but his result is not the completely general one. So he had an additional assumption of, I think, a norm on the algebra, something like this. Something I should also here I have to put the weakly in brackets. That's because the different notions for of Archimedeanness, they all coincide in the Rees-Space case. Don't worry about this. Okay. Well, and that's not all. There's even a third result I wanted to present that also fits into this general idea. This is even older by Hilbert. If we have a weakly Archimedean totally ordered skew field, and again, in this case, the weakly is not really relevant. This especially means that the positive elements are closed on the multiplication. Then it's a field. And basically what you do is, it is a subfield of the real numbers. Because you have the total order on it, you have because you have a total order, you already know it's of characteristic 0, and so you have Q inside it, and then you can just, for any element, take the...
Sorry, but in the definition of a skew field, associativity is assumed.
Here, yeah. In this case, of course, the assumption is we have a skew field, and this means associativity is assumed. So basically, this theorem only gives us the commutativity for free. Yes. Okay. So let's think for a second. What would be a common generalization? These 3 theorems, well, 4 actually, that I've shown you, there are 3 from 3 different, almost different fields of mathematics.
But not skew
fields.
Not skew fields.
But not skew fields of mathematics, no. But they certainly have a lot in common. So we always have an underlying ordered abelian group. This Archimedean assumption was always important. We always had a product and we always had the positive elements closed under the products. And then there were additional assumptions. And these additional assumptions, well, they depended a lot on the context.
Sorry, Piotr, I'm surprised that Piotr didn't point it. A closed under multiplication.
Closed under multiplication.
Would be a common generalization. What could a common generalization of these theorems look like? Okay.
So just one word missing, yeah. You found it. Obviously, I didn't miss it. I missed it on purpose so that you have something to look out for. Okay.
Yes. It has been noticed, you know.
Yeah. Will you also notice the second one? Keep your attention up. Okay, and now let's go to the general theorem. And as you said, all these results, they're basically not results, or you could interpret them as results for a multiplication on a monoid. And that's how I like to rephrase it. So first we need some basics about abelian monoids. So if we have an abelian monoid, we say it's cancelable. Well, if from A plus C equals B plus C, it follows that A equals B. Of course, if the monoid is a submonoid of an abelian group, then this is automatic. Because then you can, well, subtract the minus or add a minus C.
And of course, cancelability implies that this can be embedded.
And conversely, it implies that the monoid can be embedded in an abelian group. So basically, these two approaches they are equivalent. And we say that the monoid is unperforated. if, well, from n times a equals n times b, it follows that a equals b. This is something that is not automatic if we have a submonoid of an abelian group. I think of something like all the natural numbers with 0, but without the 1. This is closed under addition. It's a submonoid of the whole of the integers, but this unperforatedness is not fulfilled. And you already see the 1 is missing. There is somehow a hole in it. This, I think, or I hope that this is the reason why.
So in particular, if you embed it into an abelian group, which is divisible, then you can.
Yeah. Sorry. Yeah. If we are talking about a convex form of a real vector space, then the unperforatedness is automatic, because then you can divide by n, multiply with 1 over n. Okay. And on such an abelian monoid, we define a reflexive intransitive relation, or a relation, well, as a is less equal than b if there exists a delta such that a plus delta equals b. So this is basically your standard ordering on a monoid. The natural numbers would give you your standard ordering of the natural numbers, right? And I should point out the general theorem, it can be phrased without making use of these axioms, but then everything is just more technical, and I think in the end you really don't get a more powerful theorem. And so for this talk, I like to keep it a little bit simpler. And we will always make this assumption of cancelability and unperforatedness. Okay, and basically, as you pointed out, if you have a convex cone of a real vector space, then this is a cancelable and unperforated monoid. And if we have a partially ordered vector space and our convex cone are the positive elements, then this natural ordering here, that's just the original given ordering of our partial vector space, partially ordered vector space. Of course, restricted to the positive. Okay. So this is basically how we will then in the end connect the big theorem back to the earlier versions that I showed to you. Now, you remember in all these earlier theorems, there always was one additional assumption that depended on the context. And we will also need an additional assumption, and this is the localizability. So if we have a cancelable unperforated abelian monoid and a bi-additive multiplication on it, well, we can of course define the opposite multiplication, which is just reverse the arguments. And then we say one element S is localizable, left localizable for this multiplication. Well, if this holds, whenever A and B fulfill the property that S times A plus A is less equal than S times B plus B, then we want that A less equal B. We'll come back to this in a second. And of course, this was left localizability. Then you could define right localizability accordingly. That would be the same thing with the opposite multiplication. And then we say that S is localizable if it's left localizable for the multiplication mu and left localizable for the multiplication, for the opposite multiplication.
I have a question. Usually localization means inversion of something, inverting something, okay? So here you have multiplication and addition combined in this condition. Is it equivalent to invertibility of something or inversion of something?
It has something to do with it. We come to it in a second. just let's fix this last definition. So the whole monoid will be called weakly localizable if for every element of the monoid there exists a localizable element that is bigger than this original element. So basically, if the localizable elements are cofinal in the whole monoid. Okay, and now back to your question. If we have inverses, then kind of localizability follows. So if we have an associative product, that's something we have to assume here. And if we have a unit, 1, and if the inverse of S plus 1 exists for some element S, then I claim that this S is localizable. Okay, why is this the case? So if we have AB given such that mu S, this here, such that this inequality holds, then we want to show that A equals B. So what is going on? Let's see whether I can write it down here. Now, the first thing is this axiom of localizability has been given in a technical way without assuming that a unit exists. Of course, if a unit exists, then we can write it in a simpler way. We can just use the unit. And the assumption is that S plus 1 times A is less equal to 1. S plus 1 times B. And then, because of associativity and because of the existence of an inverse, well, we would get something like, well, we can multiply this inequality with the inverse of S plus 1 to the minus 1.
But you need one thing more, that multiplication preserves these inequalities.
Yes, but it does because of the way we defined the because of the way we defined the inequality. Because what does this mean? This means that mu of S plus 1 A plus some delta equals of S plus 1 times B, right?
Okay, so this, I forgot that this is very special.
Yeah, it was not an arbitrary inequality, not an arbitrary order. We defined it in a very special way. And then now we can multiply with the inverse of S plus 1, and we get, well, A plus product of the inverse of S plus 1 with delta equals B, and this is by definition A less equal B. So what this example also shows is, well, why is this called localizability? It somehow means the ordering is localizable if it is compatible with, well, introducing additional inverse elements. So basically, it was constructing some localization. Okay. So now the general theorem. We assume we have a cancelable, unperforated abelian monoid and a biadditive product mu. And we also assume that the product is weakly localizable. So there exists a cofinal set of localizable elements. Then, well, what do we get? We get some kind of approximate, approximate commutativity and a approximate associativity.
So this approximation is by means of this equivalence relation generated by this smaller,
Yeah.
by this relation. Okay, okay. No,
That is maybe not exactly the equivalence relation you were thinking of. It's a little bit more general, right? So this equivalence relation, D is approximately E. Well, if there is some F, such that n times D less equals n times E plus F, and conversely, n times E less equals n times D plus F.
the same F.
Same F. If you have different Fs, you can just, well, add the two and then you get the same. Or then you get one that works for both, right? Again, well, if we have not some monoid, but a convex cone in a real vector space, then we could rewrite this as E less equal E plus 1 over n times F, and well, E less equal D plus 1 over n times F, or equivalently, one and this to the left-hand side, minus 1 over n times F less equal E minus D less equal 1 over n times F. Okay, if this equivalence holds if we have a convex cone in a real vector space. So basically, this shows, well, maybe gives you an intuition what this equivalence relation looks like. Two elements are approximately the same.
So the difference is infinitesimally small.
Difference is infinitesimally small, and this means if we have a Archimedean ordered real vector space, then this equivalence relation is equality. This is basically the last ingredient how we will get back the old theorems. So just some other remarks. So if we have some additive inverse in our monoid, then this thing is approximately 0. Why? So 0 approximately D. D less equals 0 plus some F. Well, this is true. We can take D less equals 0 plus some F. We could even take the F equals 0, I think. Because if we have a minus D in the monoid, then D is less equal to 0.
But 0 now is what is 0 now? We have a monoid with 0.
There's 0.
Monoid, additive monoid.
Sorry?
It's a 0 of an additive monoid, so adding 0 is like identity.
Yes. So if we have an inverse of D in a monoid, then this means that D less equals 0, because there exists an element delta, namely the minus D, that we can add to D and get 0.
Mm-hmm.
And of course, D is also greater than or equal to 0, because everything is with respect to the special order greater than 0. And what does this mean? This theorem is really about true monoids. As soon as we have inverse elements, the theorem becomes less powerful, because then, well, this equivalence relation starts to make everything equivalent. In a group, just everything would be equivalent. And then the result would be empty. What one can show, this equivalence relation is compatible with the structure of the monoid, so we can construct a quotient monoid, and this would then be truly commutative and associative. And what we already discussed, if we have a weakly Archimedean partially ordered vector space, then this equivalence relation is just equality, and then we would really get commutativity and associativity. from the theorem. Okay. How am I doing? That's fine. I think there's some time, and we can discuss how from this general theorem we can get as corollaries the old ones. And then I hope that we will also have some time for the proof. So first corollary, if we have a weak Gleichmedian partially ordered real vector space in a bilinear multiplication, and we assume product is closed under addition, we have a multiplicative unit, and this unit is an order unit. Then U is associative and commutative. So how do we get this? First thing is, because of this order unit assumption, not this here, because of this order unit assumption here, every element of the algebra is a difference of two positive elements. Basically, means that A equals n minus A. A equals A minus n minus A equals n minus A. So every element A is a difference of two positive elements. And that, of course, means if we can show that multiplication is positive, associative and commutative on the positive elements, it is positive, is associative and commutative everywhere. So it looks like we can apply our theorem. Well, we have this Archimedean partially ordered real vector space assumption, and therefore the ordering in the theorem is the ordering here, and the equivalence relation from the theorem is just the equality relation. So everything we have to do is we have to prove that the monoid of positive elements has this weak localizability property. Then we can apply the theorem, and the theorem would give us associativity and commutativity of the positive elements, thus everywhere. So how does this work? Well, weak localizability only means we need just a cofinal set of localizable elements. And in this case, we can just take the multiples of the unit. That should be that is a cofinal set, and we only have to prove that these multiples of the unit, that they are all U localizable. And this is very quick. We just have to be careful that we don't use associativity here. So what we have to show is, we want to show that n times 1 is localizable. So if n times A plus A is less equal n times B plus B, then in the end we have to show that A is less equal than B. N times unit of A plus A, this is just n plus unit times A. And well, we do not use associativity here. We just, well, count how many A's are being added on the left-hand side, right? And then because of our assumption, we are in a partially ordered real vector space, we can multiply with 1 over n plus 1. This is a scalar multiplication, not a multiplication in the algebra. And we get that A is equal to B. Okay, so this first application was quite easy.
Just to be clear, no associativity is used here simply because everything is concerned with just A. So I don't know the diagonals, so no associativity needed.
Yeah, so basically everything that's, and by definition of limits here, it's just some A's, sum of several A's, right?
It's an addition.
It's just an addition. This is just a short way to write addition, right? What is used is that we have a multiplicative unit. Okay. The next of the old results was every weakly Archimedean F algebra is associative and commutative. F algebra. Every Archimedean F algebra is associative and commutative. Now we have to, well, apply some of the respace techniques, but it's not so good. But I have to peek.
So now we are using the monoid, to a monoid. Now we are using this RIS. And these two approaches are disjoint.
We will reduce to a monoid structure.
Ah, you will use.
So first thing is, because we can separate every element in its positive and the difference of its positive and negative parts, again, the whole algebra, the whole respace is the difference of its positive elements. And we have the same thing as before. The given order relation on the respace is just our monoid order relation on the positive elements, and the equivalence relation of the theorem is the equality, because we have a weakly Archimedean partially ordered real vector space, especially. And what we will have to show is that actually every element, every positive element of the Archimedean F algebra is localizable. So we start with the assumption we have two positive elements, A and B, such that S times A plus A is less equal than S times B plus B. And we have to show, well, in the end, we have to show that A less equals B and A less equals B, well, that's equivalent to the negative part of B minus A is 0, right? A less equals B is equivalent to B minus A is positive, and something is positive if and only if it doesn't have a negative part. Right. This is something that is some, yeah, okay. So first, product of S with, well, we make some observation. Product of S with the positive part of B minus A plus the positive part of B minus A minus, well, basically the same thing, but with the negative part. Mu of S, the negative part of B minus A plus the negative part of B minus A. What is this? Well, because of the biadditivity of the product, well, we can take the difference of, no, that was not. No. Take the difference of this here and this here, and this will give us the product of, no, of S with B minus A, and then difference of B minus A positive part and its negative part. It's a bracket missing. Gives us the difference of B minus A, which is, well, basically product of S with B plus B minus product of S with A plus A, which is by assumption greater or equal 0. So this is basically an observation that we will need later on. First step. Second step, well, certainly the negative part of B minus A is positive, and we can obviously add some positive thing to it, and we will get something that's bigger. So it's less equal than product of S B minus A cos negative part plus B minus A negative part. And because of the first step, well, the first step showed us that basically this thing here is greater or equal than this thing here. But this here is just what we have here. So our chain of inequality, well, we can add another inequality. Product of this is less equal than product of S with the positive part of B minus A plus the positive part of B minus A. Last step, if we have some chain of inequalities in a respace, well, we can always take the infimum with some fixed element. This is not so hard to check, I would say. And we take now the infimum with the negative part of B minus A. So the infimum of 0 with the negative part of B minus A, well, that's again 0. Infimum of B minus A negative part with itself, well, that's just B minus A negative part. And then this thing in the middle, we just skip. We're interested in the infimum of this with the negative part of B minus A. And then we can use something like a triangle inequality. So infimum of this with the negative part of B minus A is less equal than infimum of this here with the negative part of B minus A plus infimum of this with the negative part of B minus A. So what you get in the end, the whole thing here is less equal than the product of S with B minus A. Positive part, infimum B minus A. Negative part plus B minus A. Positive part, infimum with B minus A negative part. Okay. And now this is 0 by assumptions. So this thing here, this is 0. That was a general respace property. And this here is 0. That was our F algebra axiom. So thus we have proven this thing here is also 0. And we're done. So this proves all the positive elements in the F algebra are localizable. We can apply our theorem. We get associativity and commutativity on the positive elements, and then we get it everywhere. Okay, and that's it with the respace. The respace tricks. But one thing I should stress is there was this other theorem that the Archimedean almost F algebras are commutative. And this cannot be a a corollary of the big theorem, because my theorem will always give us associativity and commutativity. And here we have seen for the Archimedean almost F algebras, there was a counterexample of a non-associative one. Okay, so yeah, this is, so basically when I heard about these theorems, my first impression was that this associativity and commutativity of F algebras, this is something, a true lattice order effect. But apparently it is not, because it's corollary of a bigger theorem. But for the almost F algebras, there the commutativity that really seems like a lattice order effect. At least I would not know of some generalization to a non-lattice ordered case. Okay. Last part, and here, now it's getting interesting. The last statement was that certain skew fields are fields. The old theorem by Hilbert, every Archimedean skew field is a field. We can get this too as a corollary, but we can actually get more. So we start with a skew field of characteristic 0, and we make this definition here. F plus plus. What is this? It's basically the sum of products of squares. So a sum of products of squares. Heuristically, this sounds like something that is positive. And if for every element in this Q field, there is a natural number such that F minus n is not in this positive F cone, in this F plus plus, then F actually was a field.
Why double plus?
Why double plus? That's my personal notation, because this is somehow something that you get from the algebraic structure that looks like something that should be positive, but it is not. So we do not assume that we have an ordering, right? It is not the positive elements of a given ordering on the field. It is something, well, that you get from the algebra, from the algebraic structure. Basically, this is something like the convex cone of all those elements that will be positive in any reasonable ordering on SQ fields. So they are really positive, independent of somehow they will be positive independently of what you actually choose for your ordering. Okay. And I should stress that I am not an expert on skew fields. I tried to check whether this result is known. I could not find something like this. Actually, there is not a lot of literature on ordered skew fields. At least that was my impression. So to the best of my knowledge, this is not known, but I'm not really an expert on the literature on skew fields. So I can't guarantee that this is not known. And if someone knows where maybe to find this result, please tell me.
Just to be sure we are on the same page, a skew field has all the axioms of the usual field except for commutativity, right?
Yes, yeah, this is important. So we do assume associativity. So the only thing we get from as a corollary from the theorem is commutativity.
Okay, so quaternions would be an example of a skew field, right?
Yes. What happens for the quaternions is, well, in the end, you will be able to write everything as a sum of products of squares, because you have them. Well, as soon as the -1 is a square, then everything then basically everything is a sum of squares. So again, we want to apply the theorem.
I ask a naive question. Why it is not enough to consider sums of squares simply?
Because this is then not closed on the multiplication. At least not with others.
So you need this f plus plus to be multiplicatively closed.
Yes, this will be important later on. So the first step, like always, the whole field is a difference of its, in the sense, positive elements, because everything can be written like this as a difference of two squares.
So this will be your monoid.
So the f plus plus will in the end be the monoid to which we apply the theorem. And also, this was our first example of localizable elements. Every element in this f plus plus is localizable because we have the inverses. And this is where the this is where the being closed on the multiplication is important. So we can apply our theorem, but our theorem only gives us, well, product of A and B is approximately product of B and A. So we have to understand this equivalence relation. So we will show that C approximately D means C equals D. Where is it? Ah, and for this, we need to introduce something to this that I know as the double dagger of this cone. Probably there are many different notations, and people in different fields have considered this construction under different names. For me, this is all the elements E in the field in the surrounding abelian group, such that there exists an F in the field such that F plus N times E is in F plus plus for all natural numbers. And this is basically a cone, a submonoid of F that is somehow a little bit small, a little bit bigger, right? So every element of F plus plus will certainly be in there, because then we can choose F equals 0. And this thing is important because
don't you assume that F must belong to F plus plus?
No, but
arbitrary.
Basically, it doesn't matter. Because every element is a difference of squares. So we can basically always, if we have some F that is not positive, we can always find something that is a little bit bigger and is positive. And then, well, if you go from F to something that's a little bit bigger, this relation will still be valid. But this is a good observation, because I assume you already know what I want to do. C approximately D is equivalent to, well, to Z minus D in the intersection of F plus plus. Double dagger with minus F plus plus. Double dagger. This is basically just application of the definitions.
Wait a minute. So before, double dagger was defined for this positive part f plus plus. What is this dagger plus for minus f plus plus?
Sorry. Typo. It should be more something like this. How it makes sense.
Okay.
Okay, just to have everyone on the same page. Why does this equivalence hold? C approximately D means there exists, well, actually, no, it means there exists F such that F plus N times C minus D and F plus N times D minus C are in this right. This was basically our definition of this approximate
Frequent expressions f plus n times d minus c. So I cannot.
F plus N times.
Yes, yes, this is the second one. So this is plus.
This F plus.
Plus.
It doesn't get better. F plus N times D minus. Okay, the original definition was there exists, for this approximate was there exists an F such that D is less equal than, such that N times D is less equal than N times C plus F, which then is equivalent to, well, F plus N times in brackets C minus D is positive, and well, vice versa. So let's erase this here. Oh. No. Full. Now the point is this intersection of F plus plus dagger with negative of F plus plus dagger. This is an ideal. This is an ideal, and this means it's either 0 or it's everything. Now, why is this an ideal? Well, it is closed under addition because it's the intersection of two monoids. Well, it is even a subgroup because, well, for everything it will also contain its negative. Problem is, why is it, well, why is the product of anything, any A with an element in this subgroup, again in the subgroup? Basically, this is some kind of, you could say, some polarization trick. Any element is the difference of two squares, and this thing multiplied with a square will be in this wannabe ideal because the F plus plus was closed under products. And well, one has to be a little bit more careful because we have the double dagger here, but it's not so hard. So basically it is some polarization trick using that everything is a difference of squares. Okay. And then we have these two options. Either this is a 0 or this is whole F. Well, if this intersection is whole F, then we will for any F find something such that F minus N is an F plus plus. Because especially if this intersection is whole F, then this especially means that the unit is in there. And this means that especially one is in here in the minus f plus plus dagger. So basically, this implies that the, or equivalently implies that the minus one is in f plus plus double dagger. And now if you look at the definition, minus one in f plus plus double dagger, this means there exists an f such that f minus n is an f plus plus double dagger for all natural numbers. This is exactly the thing that we excluded here.
Ah, it doesn't.
So this condition here, this is just made to exclude this possibility. And with this assumption, we get that this intersection is the zero ideal, and then we're done. Okay, cool. I don't have much time left. So unfortunately, I cannot tell
5 minutes.
Yeah. Unfortunately, I cannot tell you a lot about the proof, but I can give you a rough idea. So here again, here's the theorem. Cancelable unperforated abelian monoid and the localizability assumption. And we have to prove that we have this approximate commutativity and approximate associativity. And well, the first thing is cancelable unperforated abelian monoid means we can just construct the group of differences. And then we basically work with an, well, partially ordered abelian group. And we can always extend the multiplication to the to this group of differences. This is not a problem. It will be well defined. And then we kind of follow the proofs of many of these earlier theorems. They were typically representation theoretic. So we want to represent this ordered group G of differences by real valued functions. And then we hope that the product will actually be in this representation the pointwise product, which is associative and commutative. But of course, this is problematic. I mean, this would be a very strong representation theorem. And this is also not true. So this does not work. What you need for this type of representation theorems is always some kind of boundedness assumption. But actually, this is not a big problem because we do not really want to represent the whole group. It is completely fine if we could find a representation of the subalgebra that's generated by these important elements, 2 elements or well 3 elements. If you could find a representation for this subalgebra, then well, yeah, we would be done because the associativity relation holds in the whole monoid, of course, if it holds in some monoid that contains these elements. And we can go even further. We don't really need the product of, or we don't really need arbitrary products of A, B's, and C's. What we have here, well, that's just products up to 7 second order. So basically, everything that we really need in our represented space, this is maybe the A, the product of B and C, the product of A and B, the C, well, this double product and this double product. This is something like 6, 7, 8 elements. If they are in our representation space, then we are fine. And of course, then the subgroup generated by these few elements, this is not closed under multiplication. So it will not be, so that means our multiplication would only be partially defined. But if we could find a representation for this group generated by some finitely many elements here, with a partial representation, then it would be enough to conclude associativity and commutativity. So basically the idea is we represent a finitely generated subgroup that contains well, some products by real-valued functions with pointwise operations, and we hope that the original mu will be in the representation somehow the partially defined product, but it's still a product of the pointwise product. Okay, what should the point of this representation space be? And there's, again, these representation theorems usually go all the same way. One possibility is to take the normalized extremal positive additive functionals. Of course, this normalized, this only works if we have a unit. If not, then everything is a little bit more tricky, but let's stick with the unital case. And the non-unital case is just more technical, but everything works there too. And well, so basically, what does this boil down to? We have to prove the existence of extremal positive additive functionals, but in the end, as I explained, only on some finitely generated ordered Euclidean group, and this is not a big problem. And then we have to show that these extremal functionals are multiplicative. And this is where the big magic happens, and this is also, well, yeah, where we have to invest some work because of this notion, extremal positive additive functionals. This doesn't have anything to do with multiplication, right? So on the one hand, if this works, then because this representation space is what was constructed independently of the multiplication, this already shows that we can gain information on the multiplication from this representation space. But on the other hand, of course, if this doesn't have anything to do with the multiplication, why should these things be multiplicative? Okay. So I won't show you the proof. I just want to mention, you know that this works if you know the representation theorem for commutative C-star algebras. Because there too, you can choose the pure states as the representation space, right? So for commutative C-star algebras, one knows that the extremal positive additive functionals are multiplicative, but we have to, well, generalize this a little bit, and then we get the theorem. Okay. That's it. I think I have some more slides, but that was details about the proof. I don't have the time for it. What about this unit? Why is there so much in here? Ah, yeah. And here, just for the record, this is all the references, basically the references to the old results. Thank you very much for your attention.
Thank you so much. Any questions?
I have a question. You started with pointing out that if you have this unit dominating every other element, then you can construct a norm.
Mm-hmm.
Can you construct this norm such that you obtain a sister algebra in such a way that your positivity becomes usual positivity in sister algebra?
Yes. So in the setting of this first theorem, yeah. So their theorem, this theorem there basically says that with a little bit stronger notion of Archimedeanness of the ordering, then this real algebra with its different ordering is isomorphic as an algebra and as an ordered vector space to a subalgebra of the continuous functions on a compact Hausdorff space with the pointwise product. And basically, then you see that this in the representation, you see that the ordering or the norm that you can construct from the ordering, well, that's just the subnorm, right? So this is the C star norm. So it is, yeah, it is just a different version of the Gelfand-Leib axiom, if you want.
Okay, thank
Anybody else? Adam? Oh, wait. Sorry, but I cannot hear you. You please try to speak to a microphone.
The same theorem mentioned just before. You said that in the proof you construct a norm, but I wanted to ask whether or not this norm is multiplicative with respect to mu, because that was not mentioned, and the
You
moment
mean
I
more
saw
like submultiplicative, right?
Submultiplicative.
I wouldn't expect the norm to be ever multiplicative except for scalars, but you mean submultiplicative, right?
No, but for
yeah.
periodic things, and this
Yeah,
norm is
Okay. Sorry.
when I saw the Archimedean axiom, my first question that popped out to my mind was the notion of norm versus the notion of valuation. Because yeah, valuation is norm plus it is multiplicative. And well, it's defined on fields, as Adam mentioned. For example, the p-adic fields are fields with valuation, but these are non-Archimedean, while here we would have an Archimedean, and that's why I wanted to ask about the relation between this norm and mu and how it compares with your general result, because well, the last comment you made was whether or not these functionals are mu multiplicative, and yeah, I don't like cliffhangers, so.
Okay. So in this first of the all theorems, yes, the norm that you could construct that would be submultiplicative, it would not be multiplicative, of course. And basically this, in some sense, this follows from the assumption that the positive elements are closed under multiplication, and then it's an exercise. And yeah, well, about the proof of the general theorem that I did not show the theorem, the details. Yes, so you can show in more generality that the extremal positive functionals are multiplicative with a proper normalization, and what you need there is of course, is then the localizability of the ordering. This is the additional assumption that you need in this more general case without the order in it.
Okay, thank you.
Adam, did you want to ask a question?
Yes. Also, my question is also about those extremal points and being multiplicative. So in the case of C-star algebras, every pure state, which is an extremal point of a set of states, turns out to be a Dirac delta functional. So from this follows multiplicativity. So somehow one could argue that this multiplicativity is somehow an accidental, but also there is an abstract proof which can be found, as far as I know, in Caddison Ringrose book, which shows multiplicativity without invoking the precise form of this functional. So my question is, in your case, what is the situation? You have a precise form of this extremal point, or you somehow abstractly infer that those are multiplicative?
It's abstract. So you just use the definition of what it means that the positive functional is extremal, and from this you prove the multiplicativity. And you mention the book of Caddison. I assume it is actually this one.
No, I just mentioned this two-volume book of operator algebras.
Ah, okay, then it's a different one.
You mean
But
Caddison
basically
Ringrose,
this
right?
is-
Yeah,
this
Caddison
is-
Ringrose. Yeah,
Ah,
Caddison Ringrose.
yeah, okay. So I just assume that the proof you are talking about is basically the one he has in here, and this is this is where the first theorem about the ordered real algebras with the order unit comes from. So this comes from this here, and I think Wernicke, Klein, Toffbin, they were earlier, but I think they only had the commutativity. Here he also has the associativity. And basically, yeah, he has this abstract proof that the extreme and positive functionals are multiplicative in this more restricted case. So one needs a little bit more work to if one wants to get it to work with the more general case where one makes use of the localizability.
Okay, thank you.
Anybody else? So let me wind it up with a philosophical question. Why on earth did you get interested in it? How did it pop out of non-commutative geometry, non-commutative topology, deformation theory, whatever?
Well, I think that there are two reasons. So I started in my PhD, I was doing deformation quantization.
Yes.
And the project was basically about non-formal deformation quantization, which basically means we were looking at, well, we were working in a setting of locally convex star algebras, and we were trying to understand, well, can one prove general theorems for locally convex star algebras? Maybe in a similar way to what you can do for C-star algebra, but of course we were not expecting so much.
Mm-hmm.
And then it turned out the locally convex setting was maybe not so good, but I got interested in the ordered setting. And I got interested into this because of these results that people were proving for vector ordered algebras, for lattice ordered algebras. And this is where I first found these results about automatic associativity and commutativity. And of course, then I thought, well, if they prove they are basically always commutative, then it's not interesting for deformation quantization. But these things were in the back of my head. And well, I found these results surprising. I like them. And then there's this other point of view. If you want, my personal favorite approach to the Gelfand-Naimark theorems in the commutative case is constructing the representation space as the pure functionals, as the pure states, for which you need this multiplicativity of the pure states. And last year I presented to you a generalization of this theorem to an unbounded setting. And there also was some localizability assumption for the order that one needs for a commutative Gelfand-Naimark theorem in a non-bounded setting. And at some point I just realized, well, that there I also had this a theorem about, well, automatic multiplicativity of these extremal functionals. And I realized, well, the proof does not use the associativity and commutativity. And then basically I started to connect the
dots.
The two steps, yes. And I realized, well, this is actually something bigger.
And can you foresee any applications or benefits for operator algebras out of your work?
Well, I think no one will ever use this theorem in order to prove that something is associative or commutative. I mean,
okay.
In deformation quantization, it is typically said associativity getting associativity, this is a tricky
Yes.
step.
Yes.
This is where all the problems are. But
Yeah.
you will never use this theorem to prove associativity. I'm quite sure of this. But I
But
think
why
it is-
not? Why not? Is it obvious?
It is just a feeling. I don't have an example
Okay.
where you,
Okay.
I mean, how do you construct an example where you have this localizability assumption fulfilled, but it needs to be an example where you don't know, well, immediately that it's associative. I mean, I just wouldn't know how to cook something, some example where it's easier to use the theorem than to just check associativity.
Okay. Okay.
Typically, if associativity holds, then you can check it, right?
Mhm.
But I think this is important in a different sense. I mean, it shows, so people were looking at, or still are looking at ordered algebras and ordered rings. And of course, there are a lot of results in the commutative case. And then people also want to progress to the non-commutative setting. But what this theorem basically shows is not only in the lattice ordered case, in a very general case, you probably should, if you're discussing ordered non-commutative rings, you probably do not want the positive elements to be closed on a multiplication, because this is, then you're already quite close to the theorem being applicable.
Yeah.
Right? So the correct, or the, in my opinion, correct notion of an ordered non-commutative ring would be an ordered star ring, where like for the usual ordering you have on C-star algebras, you only have the ordering on the Hermitian elements. And of course, for C-star algebras, you know that a convex cone of positive Hermitian elements is not closed on a multiplication. But it has a different important axiom. It's a different important axiom. This is, okay, I think, can you read this? If A less equal B, then
Yes.
C star A, C less equals O. C star B, C. So, okay,
I know what you want to write. Yes, they're very useful. Yes, and true.
This is basically, this is the, this is the important axiom, or the non-commutative axiom that you want to use. That the cone of positive elements is closed under this, well, conjugation, or sandwiching, yeah.
Yeah. Yeah. Okay, so I think it is time to thank Matthias again. Danke schön, thank you so much. Let me stop recording.